Okay. Yeah, no, Ahmad, hold on. We'll share the speaker introduction and then you will share. Otherwise, it just goes away. Okay. So let's get started in the final day afternoon session. It will be presented by Professor Ahmad Abdelfattah. He's a research assistant professor at the Innovative Computing Lab at the University of Tennessee. Received his PhD in computer science from KAUST in 2025, where he was a member of the Extreme Scale Research Center, ECRC. His research interests span high-performance computing, parallel numerical algorithms, and general-purpose GPU computing. He currently serves as the principal investigator of the Magma library, and he has been acknowledged by NVIDIA and AMD for contributing to their numerical BLAST libraries, QBLAST, and RockBLAST, respectively. So today you'll be talking about this heFFTe project. I indicated that yesterday in my talk. We have been collaborating with Ahmad, Yifeng, Samir on a joint NSA project. So we'll be talking about heFFTe, highly efficient FFTs for Exascale Systems. So let's welcome Ahmad.
Yeah, thank you, Dr. Panda, for introducing me. And good afternoon, everyone. Sorry I could not be with you in person today. So let me share my screen and see if you, let me see. So do you see the slides?
Yeah, please go to the presenter mode. Yeah.
Okay, that's good.
Yeah,
okay.
That's good. Yes.
Okay, so I'll be presenting an overview about the heFFTe library and the joint grant that we have with Dr. Panda, Dr. Samir, and Dr. Yifeng. It's a big project, and we have some exciting performance results to share with you. So before I get started, I'd like to give proper credit to all the team members that have been working on heFFTe over the past few years. heFFTe is an ECP-funded project, so it started a little bit later after the ECP kickoff. So several members from UTK have worked on this project, several of which have moved to the industry. So the current members would be myself and Natalie Beams. However, there is one name that stands out and would like to highlight him, and that would be Stan Tomov. So Stan was the head of the heFFTe project. He was my direct boss for 9 years before he moved to NVIDIA, and he tragically passed away last fall. And I would like to honor his legacy and say that we have held a workshop at UTK in honor of his memory and his impact on the field of GPU computing. He was among the first pioneers to leverage GPUs in scientific computing. And yeah, I think the ripple effect of his work are still tangible to this day. So I just want to take this moment and honor Stan's memory and legacy. So going back to my talk, so I'll begin with a high-level introduction of heFFTe as a very flexible library to do distributed FFT computation at scale, the current status of the library, and then the joint grant that we have with the ENVA-Pitch team, the Tau team, and Yifeng about using heFFTe as a benchmark for MPI implementations. We will have some promising performance results with ENVA-Pitch and Tau, and I'll conclude with some open directions. So to begin, so I think everybody is familiar with the FFT. It's one of the top 10 most important algorithms of the past century. So it's an efficient way to compute the discrete Fourier transform. So if you have a signal X in the time domain, you can transform it into the frequency domain using this formula here. I think many of you are familiar with. And the naive way of computing this is you just organize the input signal X into a vector, and then you have these exponent coefficient laid out in a matrix. You will end up with a dense matrix times a vector. So it's a matrix vector multiplication problem. It's a very well-known routine in the field of dense linear algebra. It has order n square complexity, so it's basically memory bound. We know these operations very well. They are heavily studied and optimized. However, FFT is an elegant algorithm that brings the complexity down to order n log n. So the problem becomes even more memory bound. So this operation can never reach the computational peak throughput of the hardware, CPU or GPU. The performance is pretty much bounded by how fast you can move data around from the computing cores and the memory system. And similarly, the inverse transform is a very similar formula to the one on the top, with just some minor modification and scaling factors. So that's FFT at a glance. So with the kickoff of the ACP project, there has been some applications that required a robust implementation of the FFT at scale using GPUs. So most of the machines that came out of the ECP are GPU based from NVIDIA or AMD or Intel. All are GPU accelerated and all required some form of FFT support at scale. So this is a short list of some of the applications that sparked the interest in having a modern library that would implement this kind of functionality with robust support and of course to be forward looking. And that was the birth of the heFFTe library. So it stands for highly efficient exascale FFT for heterogeneous architecture. It can provide 1D, 2D, and 3D FFT computations. It is built from the ground up to take advantage of GPU systems. So the way it is designed that we don't do 1D or we don't do FFT kernels. We don't do the computational kernels. We try to leverage the vendor support of the 1D FFT on a single node. So we interface very well and very robustly with FFTW, coFFT, rockFFT, and 1MKL so that we leverage these optimizations that are coming out of the box from the vendor side. And then we build on top of that, a robust layer of the MPI communication and the distribution of 3D domain over distributed system. However, we need some kernels, simple kernels that do not do any compute, but rather do some data transpositions and reshape so that we can implement a multi-dimensional FFT. So the way it works in this figure here, we start with a 3D domain as an example, and it's evenly distributed across MPI ranks. We start with a reshape so that the data are contiguous in one direction, and we can do a 1D FFT in one dimension. Then we do a global transposition in another direction. We perform a 1D FFT, and then we do another global transposition and a 1D FFT, and we end up with the same 3D domain, but in the frequency domain this time. So this is a very broad, of course, dropping a lot of details here, but this is the broad idea of how heFFTe implements a multi-dimensional FFT. And since FFT is pretty much very, very memory bound, we are heavily dependent on MPI communication. So anything that happens in the MPI library in terms of optimization will propagate right away to heFFTe. So after the closeout of ECP, we are still keeping support for heFFTe. I would like to give credit here to one of our collaborators, Miro Stoyanov. He is at Oak Ridge National Lab, and he's keeping the project afloat. So we had one release since last year with support to different CPU backends and all the major GPU vendors. So heFFTe can do multi-dimensional FFT with complex transforms and real transforms as well. So there is flexibility in the way that you provide your transform, or you would like to perform your transform. There is support for sine and cosine transform, and this is very important for some of our work with InvaPitch, and I'll come to that later. It can do batch FFT concurrent independently, and it has many knobs and controls that you can play with so that you can get the most out of your underlying backend. So you can get the most out of MPI, you can get the most out of your backends or the network. So heFFTe is open source. It is well integrated into the XSDK. You can install it from the GitHub repo, or you can install it through SPAC. So it is within the ecosystem of the DOE scientific software. And again, there are no major developments. The work is pretty much done, but we would like to exploit heFFTe in another domain as a real-world benchmark for MPI. On the right, you will see a little bit old slide because we are showing here results on Summit. But you can see that heFFTe is because of the robust support for vendor backends, we can easily achieve performance portability moving from Summit to Frontier, and I'll show some results on newer systems as well. And because the compute is not really the dominant component, most of the performance will be like similar to straight lines because it just scales with the network bandwidth. This is another slides, maybe need a little bit of an update. So just to show here that heFFTe is among the very flexible libraries out there. So it can do a lot of stuff with your FFT, and I'll come to that later. There are so many controls that you can tweak in order to achieve different performance levels at the same hardware. So this is some stats about how MPI is dominating the execution time in heFFTe. So these are 2 runs on Frontier. So Frontier is an AMD system with MI250X GPUs. I use here heFFTe's own minimal tracing tools. So there is a tracing tool in heFFTe that you can use without any dependencies. So on the left side, you will see an 8-node runs, and each node has 8 logical GPUs. So we ran 64 ranks in total and 1 rank per logical GPU. And you can see that using all-to-all V, it's almost 80% of the total execution time, while ROC FFTe is using just 17% of the time. And if you push it a little bit further to the right, at larger scale, 64 nodes, 512 ranks on 512 GPUs, we are approaching almost 90% of the execution time on MPI, and the actual compute is just taking 5.5%. So that gives you, a grasp of how dependent heFFTe is on communication, because it's very it's not demanding in terms of compute power. This is another trace of the 8-node run that I showed in the previous slide. You can just see that everything that's green, it's the 1D FFT. So we're here launching the kernels from the backend, which is ROC FFT in this case. And the blue navy color, excuse me, the blue navy color is MPI, which is dominating again the execution time of the transform. So that's about heFFTe being very heavily communication bound. In terms of scalability and flexibility, heFFTe provides different ways of leveraging performance. So on the right here, you will see a complex graph. It's solving the same problem. So it's a 3D FFT with a 3D cubic domain where the dimension is 1024. We are using the ROC FFT backend, and we are showing results using Cray Impage. So this is the system MPI on Frontier. So the same problem in heFFTe can be computed in 32 different ways, and that's just to show the flexibility of heFFTe. So heFFTe can do 4 different computational communication patterns. So there are 2 modes of collectives, all-to-all and all-to-all V, and there are 2 ways of doing point-to-point. So the point-to-point, the default one uses send and I receive, and the pipeline using I send and I receive, with some tricks to pipeline the communication. So there are 4 different communication patterns. There are 2 different ways of doing the composition of the 3D domain, pencils versus slabs. You can do two modes of how the 1D FFT is computing on a single node. And of course, if you have a GPU-aware MPI, we can take advantage of that. In fact, this is the default way in heFFTe. So heFFTe will leverage GPU-aware MPI by default. If not, then heFFTe can work as well with standard MPI. So again, if you multiply 4 by 2 by 2 by 2, you will get 32 different configurations for the same problem in heFFTe. And so you can play with that the way you want. Sometimes collectives are faster than point-to-point at smaller scales. But the usual trend is that when you push it for scale, point-to-point usually achieves better performance than collectives. So now to the exciting stuff. So I'm showing here heFFTe with InvaPitch collectives on Mare Nostrum 5. So this is a Spanish machine. It's located in the Barcelona Supercomputing Center. It's an H100 system. So there are 4 GPUs per node. And I think the default MPI here that's GPU aware is OpenMPI. So, and we are here using heFFTe on up to 64 nodes, so 256 H100 GPUs. And you can see that the performance scales pretty well with InvaPitch versus some oscillations and fluctuations in performance from OpenMPI. And this is credits to the InvaPitch team, especially Chen Chan. So I've been working closely with him on this machine to get this kind of performance. Of course, due to the oscillations in the OpenMPI, you can see that InvaPitch can be up to 5.6 faster than the default MPI on this system, which is a very good achievement for the InvaPitch team. And this is using all-to-all V. Now, the same experiment has been done on point-to-point. So on point-to-point, you will get better performance from heFFTe, as I mentioned before. Both libraries in this situation, scale well. However, there is still advantage for InvaPitch on this machine, up to 19% in single precision and 29% in double precision, which is quite significant for a memory-bound workload. So again, this is credits to the team at Ohio State. Now, for the latest and greatest feature of InvaPitch, which is the real-time data compression. I think you heard that talk from Dr. Panda yesterday about on-the-fly data compression. So this is done in InvaPitch using libZFP. So this is a library for compressing floating point arrays. It's mostly lossy compression. So if you look up the documentation of ZFP, it relies on the smoothness of the data. So every 4 elements or 4 to some exponent elements will be treated as a block that you compress. And depending on these data, you can control, depending on the smoothness, you can get different quality of the compression. There is support for lossless compression, and I was very much interested in that, but unfortunately, it's not parallelized and it's not supported for GPUs at the moment. So, I hope at some point the ZFP developers will be updating this soon, because this will definitely be of interest to us. Now, challenges for heFFTe to leverage data compression. So by default, this is FFT, so we're dealing with complex numbers all the time. And unfortunately, libZFP does not support that. If we run heFFTe out of the box using InvaPitch data compression, you get better numbers in terms of performance, but the accuracy is not there. So we get very large errors. It totally blows up. It's far beyond our accuracy tolerance. So this is not acceptable. However, since heFFTe is, has this robust support to do real transforms only, so cosine and sine transforms, we were able to leverage the data compression without loss of accuracy. So now we are defaulting to sine and cosine transform because of lack of support to complex numbers, and I'll come to that later in this talk. So you've seen part of this again in Dr. Panda's talk yesterday. So this is these are results on Vista. So this is a GH200 GPU system. So on the left side, you see single precision. On the right side, you see double precision. And the black bars are the default performance of heFFTe. This is the cosine transform using collectives. And we tried the data compression using 3 rates, 16, 8, and 4. So rate 4 would be the most aggressive in terms of compression, and you should expect better performance out of it. So we get up to 12% in single precision and 24% in double precision. This is very good and very promising. However, we need to understand this a little bit because ideally rate 4 should be much more faster than 24% or 12%. So we're trying to, we are actively working on this to understand how ZFP works underneath and what is the actual data size that's sent over the network after compression. We try to use tau to provide the data, but because we need more tighter integration with EnvaPitch, we are not able to extract this yet. So maybe we will be able in the future through tighter integration between EnvaPitch and tau to profile deeply what goes through the network after the compression is done. Another performance on the latest system would be on Tulumi. So Tulumi is a machine at Lawrence Livermore National Lab. It's the little sister of El Capitan system, which is the #1 system in the top 500 list. It's an AMD system with MI300A machine. And we just got cleared last Friday to share these results. So we are not able to share any results without approval from the lab. So in terms of performance portability, heFFTe again achieves about 84% improvement on Frontier. So using 512 GPUs. So from MI250X to MI300A, it's very close to 2X in terms of performance, 16 teraflops on Tulumi versus 8.7 teraflops on Frontier. And using EnvaPitch collectives all to all, we were able again to outperform the system MPI, which is MPitch at this moment. So these results were obtained by my colleague, Natalie Beams at UTK. She did a performance sweep using collectives. And as you can see, MPitch is better at smaller scales, but when we push it to 64 and 128 nodes, we were able to achieve a much better performance than the system MPI. And this is using ROC FFTe as a backend and double precision for the FFT compute. Other results on the same machine. So this is again work in progress by Natalie Beams. She is working on adding persistent collectives to heFFTe so that we can mitigate the overhead of setting up these calls. And you can see that at smaller scales, we have very good improvement actually, up to 21% performance improvement versus regular collective calls. However, this improvement goes smaller as we increase the number of nodes. And again, this is work in progress. And Natalie is working closely with the EnvaPitch team, trying to extract the most out of these persistent collectives. So to conclude my talk, I hope now that I give you a good overview about heFFTe as an FFT library that's built from the ground up to work well on GPU systems with the GPU-aware MPI. It supports all the major vendors, all the major FFT backends. It's very highly configurable. You will find the configuration that is best for your hardware. However, in this talk, I was not looking deeply into the development of heFFTe itself, but rather using it as a real-world benchmark for MPI implementation. And this is a joint project that we have with the EnvaPitch team and the tau team. heFFTe is very much memory communication bound, so it's a real-world benchmark, and it's very flexible to expose potential opportunities for improving the performance of MPI implementations. Of course, we were able to benefit from the integration between EnvaPitch and tau. So we got better performance for collectives as well as point-to-point. real-time data compression was beneficial for real transforms only at this point. We will be looking closely at complex transform. And again, the deeper integration with Tau would enable us to profile, the efficiency of data compression. So what's been actually sent over the network, not what has been passed as an argument to the MPI call. Our future direction is to look into support for complex transforms, which is the default mode of operation for heFFTe. We will likely go into the direction of splitting the real and imaginary component of the real of the 3D domain, and then merging it back when we do the transform. Profiling the data compression, I already mentioned that, and we haven't yet tested the compression on AMD systems. So we'd like to do that on Frontier and Tulumi and El Capitan if we manage to get access to that. The persistent collective is still a work in progress, and Natalie is looking deeper into that. One thing that might be of interest, since heFFTe has so much flexibility and versatility, I hope that we can manage to provide a component like a recommendation system inside heFFTe that would give the end user the best performance on a given system. I think we will need some sort of benchmark sweep on a given system and try to train some model to give the user some insight on what would be the best configuration to execute the FFTe on a particular system. This is my last slide. I'd like to thank you for listening, and I'll be happy to answer any questions.
Let's give a thanks to Ahmad. Any questions for Ahmad? Yes, Nick, please go ahead.
Hi, Ahmad. It's Nick Contini.
Hi. Yeah, hi.
Thank you for your talk. So in those results where you varied the ZFP compression rate,
Yes.
You saw a benefit between no compressions to 16 to 8, but then not from 8 to 4. So my question here is, so I believe that the rate, that number means the amount of output bits per element. And so is it possible that that lack of performance increase between 8 and 4 is due to you being at essentially these sub-byte, output elements, and thus maybe the hardware support, there's not like an efficient implementation to, take some value and then output a 4-bit value, if that makes sense.
Yes. So that makes sense. So as you can see, there is a little bit of a drop between the blue bars and the red ones. It's a very slight. So this could be what you are explaining here, but I wish we can, profile, the overhead of the compression itself. So I'd like to see, because here the compression is done pretty much on the GPU probably. So I would like to, profile the kernels. Maybe the kernels that do rate 4 are slightly slower than rate 8 because of the sub-byte access, or maybe it lacks some tuning. So it's really dependent on how efficient the ZFP implementation is. Yeah, so that could be it. And of course, profiling the compressed data itself and what's being sent would be very insightful.
Thank you.
Any other questions?
Yeah, Ahmad, you mentioned that you were seeing some performance enhancements from using persistent collectives.
Yes.
Can you kind of tell us how you're using those? And if you guys have, I know you said you haven't been able to really break this down yet, but if you have any initial intuition on what's giving you that benefit?
So, so all the details will be with Natalie. I'm not familiar with the deep details of that. So we need to call the collectives multiple times when we do our transforms. Okay, so because it's at least for 3D, it's at least 3 times. And if you probably will need the inverse transform, so you will have also, multiple collectives after that. So if you set this up one time, you can use the same context to execute the subsequent calls for all to all. and that saves some time. So Natalie was not able to grasp the performance behavior at scale and why it goes down. I should also point out that this is not the latest from EnvaPitch, so we were not able to get the latest build because Tulumi is a little bit restricted. So we would like to try the latest release from EnvaPitch and see if we are able to get better performance.